Alright, I think I'm making a video. Draft Science presents and such. So I think this might be a series also. Something like Dissident Dumbass of the Week award goes to, this week it's Decini.com, or it's some sort of ethereal mechanics, something like that. Anyway, yeah, right there it says it, ethereal mechanics. Oh my. So anyway, Ether Nutter, I suppose. But anyway, 2 videos, just plain stupid. So I'll just play through clips of this. So the paraphrase is he's made apparently a software program, who knows how much of that is original content, in which you can duplicate the slit experiments. And I would argue that it's by some really bad generic math that doesn't reveal the real pattern at all in its real form. So it's just fake physics, it's just junk. And you ought to demonstrate before you demonstrate that you have accurately diagrammed the reality before you present something. I mean, even this idea, like, it's a nice idea to be able to see the pattern on a curved surface, but it's clearly he's done something wrong in the formulas he's put into his software, because the distortions are insane in terms of bending the projection screen shouldn't create as much distortion as it creates. So yeah, like I said, we'll just jump through some of this.
How wide the screen is, this screen out here is going from minus 180, minus 90 to plus 90 as far as azimuth goes. Okay, so that is the...
Yes, that's the right way to view it, is at equal distances. But again, like I said, I don't even know why he has these green things at different widths. The whole thing doesn't make any sense, but whatever. Play a little bit more.
Parameters that are being displayed here. So let me show you the difference. This is the, this is the front of the box. This is the back of the box. And let me show you what it looks like when I put it curved.
Right, and so I don't know why the software does this halo effect. It's just cheating some more. And in terms of the disproportion, it should be even. Presumably the light should be much bigger than the slits, so we should be able to get nice, consistent bars. Blah, blah, blah.
Screen it. You see, you get much more of the field of view because now you're looking completely from left to right along the screen.
And again, that shouldn't be that dramatic a difference where you couldn't see it at all before. Bending the screen shouldn't consolidate that much unless he's bending a screen that's 2 inches away from the slits, which isn't very practical. And clearly this pattern doesn't match what the pattern would be at these measurements. So just, not even close to the reality.
As I increase the width, you'll see that the fringes darken toward the center.
Yeah, so which isn't the truth either. So as you make the slits wider in the 2-slit experiment, just like the single-slit experiment, you get more pattern, not less pattern. So clearly he's screwed this up somewhere. The most dramatic visualization of the screw-up, he's using the same math, for the double slit and the single slit, which you can't do. So here he pretends to make the double slit into a single slit, and even concedes that what he's really doing, because there's an artificial line in the screen, is converting 2 slits into 1 slit, which you can't do.
I don't know if you can see the camera. I'm looking and I can barely see him.
So there's a little line in here, and he even points out how
right up close. Let me see if I can zoom the camera in.
The little line is an artifact. So let me see if it does the
in the drawing
artifact
program, because even though there's no gap, I'm still drawing 2 rectangles to represent the 2 gaps squashed together, and there might be a little bit. That's just a round-off error.
Right, it's just a round-off error. It's a complete mistake in the sense that the math for the single slit is different than the math for the double slit, and the dimensions of the slit are what's important in the single slit, and the dimension of the impediment is what's important in the math for the double slit. His pattern also doesn't have the double pattern, which is the rules of the double slit, because yeah, the math, most of the obvious math, doesn't include what you actually get as a pattern, which is the envelope idea, where you have two patterns. You have the bar pattern and then a separate pattern of bar, groups of bars. So it doesn't do that accurately. So what's the point? What's the point of doing a simulation that doesn't accurately portray what actually happens? I mean, what value is a misrepresentation of the reality? And you can see it when he does this single slit. He doesn't get any pattern, and you know, nothing like the real pattern.
You see the side lobes now.
I mean, obviously this is nothing like what you get with the single slit.
And then it comes to a point where your beam doesn't get any smaller.
Nothing like it at all.
Well,
you know.
actually, in this case, that is the problem.
I mean, this pattern is not even a pattern you're going to get at all, ever. Clearly your software doesn't work. I mean, this is the single slit. It's just a blob. Obviously, again, because he's basically taken one of the variables out of the equation, because he's using double slit math to do single slit diffraction, and you can't do that. You have to change the variable. So now he's back to double again. So we'll just play some of this single part just because he's just rambling. You know, and it's all this bullshit. Oh, for the Patreon people, I'll give you the source code, and for the this, and you know, just all this gimmick bullshit. Try to extort money out of people. Instead of just saying, look, I'm trying to do good science, would you try to give me some money so I can do some more science? Instead of just an honest to beg for money, it's this stupid extortion. I'll bribe people. Oh, please, I can give you the source code. Really exciting. And then you can fix it. Because, yeah, obviously it's a piece of shit. I hit the play button. I guess he's not talking at the moment.
Yeah, I can't tell if that thing's focused or not.
It doesn't. Your focusing ain't going to help it.
You can see the side lobe. I have to double check it when I look.
So again, we know that there's nothing faint about the lobes in the single slit. You know, you can get 40 little bars. You can get 40 of them. No problem, easily. And so obviously this software is garbage. And, you know, it's just more junk science. Just, you know, people are, you know, there's just no point in doing stuff that's wrong, you know, that's real knowably wrong. I mean, it's not like it's a difficult subject to know, because you can just Google single slit and you can see, wow, yeah, look at all that bars. I mean, yeah, obviously my math must be broken because I'm not getting all them bars. Alright. Moving on to his other stupid video. Alright, so Crookes radiometer. Now this is always, you know, that's always an interesting subject when any physicist starts picking at that, you know, it's a little thing that spins. Interesting. But
Wheeler has come, what I think he's come to the right conclusion.
So he's sitting there doing this Ken Wheeler crap. Like Ken Wheeler has the right idea because he thinks it's a bunch of electrons being shot off the surface by ultraviolet light and blah, 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 and all this just nonsense. I mean, first, that happens on reflective surfaces like metals. And there's no reason to believe that it happens more on surfaces that have been blackened. So, because that's not metallic, then it's paint or something else on the surface. And you're not going to get the same effect depending on the material you're exposing to the ultraviolet light. You're going to get more or less of that effect. So then he uses these filters to shine white light at the radiometer, claiming that somehow he presumably is thinking that he's, you know, not harming the quality of the light he's filtering. I mean, you really should have an actual source of ultraviolet or an actual source of infrared if you want to do it right. But regardless, So there is lots of content on the internet to find, regarding radiometers. It's conversation happened with Maxwell, and it's got a whole history, and the debates that went on 100 years ago, and people have done the experiment. So as a premise of this video is somehow he's saying that people haven't done the experiment, that we don't have enough information or something, and that he has to draw these wacky conclusions, which isn't true. And yeah, the Wikipedia page might not be 100% correct, but the fact is there is stuff out there that will show you the experiment done. So then he solicits an Amazon wish list or something, because he wants people to buy him a vacuum jar, bell jar, whatever they call them, so he can put that thing in a vacuum, a stronger vacuum, and prove Ken Wheeler right, which he won't do, because if you put it in a stronger vacuum it won't spin, because people have already done the experiment. So I'll show you a video of somebody who's already done that quite effectively, in the sense that you can see the experiment done, and it's kind of undisputable that this effect is something that happens in a specific circumstance and not in any general circumstance. Too much air, it doesn't work. Too little air, it doesn't work. So obviously it has something to do with something a little more complicated. Alright, so he makes lots of errors in this video. So he shines the flashlight on it, and it spins really, really fast. And obviously when he puts the different filters, the red, green, and blue, it spins a lot slower, because obviously he's blocking some portion of the radiation. But it still spins with the red one, and it spins a little faster with the blue one, but it spins insanely faster with the complete white light source. And then he has this theory that that this is about the infrared radiation not being what's the right way to say it? That somehow the thing is radiating, because black surfaces radiate heat, that somehow infrared should be more effective. When no, that's what they're radiating, because they convert energy in one form into energy into another form. So the black surface would essentially absorb ultraviolet light, and it would emit it at infrared light. It doesn't mean it's more sensitive to infrared light, it just means that that's what it's going to produce, okay, when it essentially gives back the momentum, in the opposite direction. The equal and opposite reaction finally takes place. It's going to take place as an emission of thermal, infrared. Just like the Earth does with the greenhouse effect, in the sense that, the ultraviolet radiation comes in, and the Earth is at equilibrium, so it's going to give back all the energy, but it gives it back as infrared, as heat. So it's just a stupid assumptive argument, that somehow it should be more sensitive to infrared, when of course no, it shouldn't. What goes in has nothing to do necessarily with what goes out. So we'll play some of this, and then we'll get to the ending, or the demonstration of how this theory is. Well, here he's just sitting here trying to spin it. It spins.
It says with red light it won't spin, and this here shows that's not correct. But that does not defeat.
Right. So Ken Wheeler is saying that it doesn't spin with red light, which clearly is wrong. So it does clearly spin with infrared radiation, or red light, visible light. It will spin, and if you cool it, it'll spin in the opposite direction, which is obviously it's another indication that this has something to do with thermal, which has something to do with the transmission of energy from one place to another, in terms of its R factors and all that kind of stuff, which has to do with the density of the particles and all of that. So clearly that's what this has to do with. But anyway, so it does clearly spin. So Ken Wheeler's clearly wrong. This isn't the photoelectric effect. This isn't because electrons are being shot off of the black surface and they're not being shot off of the metallic surface.
What his theory is. Okay, red light will make it spin, but it spin It's almost doesn't even want to spin, but bright enough red light will in fact make it spin.
Right, and we already know that red light is at a wider, longer frequency, at half the, it's twice as big as the blue light. So obviously the amount of energy that is quanta you can deliver in the same amount of time is doubled for the blue light. So that's why it goes twice as fast when you use the blue filters, because the blue light has twice as much quanta in it. Just the way it works out. But that has nothing to do with the photoelectric effect, which is more to do with the fact that you have to push electrons out of their tension, which means you have to hit them with a certain quickness. You have to fire the bullets quickly.
It's going to spin up at a much higher velocity.
So this is part of the conversation that's never talked about, so I'll just mention that briefly, just because I've sort of pointed at it before. So they talk about the photoelectric effect. The Baldy Katz said it in his video, that somehow the theory is that ultraviolet light delivers a punch, a bigger quanta. And it doesn't deliver a bigger quanta of energy. It delivers more quantas of energy in a smaller amount of time, which is the key to tipping something or pushing something, before it rebounds. So if you want to get more bounce out of a trampoline, for example, if you were throwing things at it, throwing something, say you stick a baseball on the trampoline and you want to hit the baseball again, and you want to see if you can get the baseball to push back more, get a bigger reflection. Well, it means you have to hit it while it's still depressed, and then you hit it again to depress it more, and then you hit it again to depress it more before it rebounds. And that way you get a bigger rebound. And that's the idea of why ultraviolet light pops electrons out, is because it delivers more quanta quickly, keeps pushing an electron into the tension, that is the tension between the other electrons. There's 3 electrons, let's say, and if you want to push this one down, the other 2 are going to push it back up. But if you push it fast enough, it doesn't have time to rebound, so you push it deeper into the pressure with the other 2 electrons, and that pressure with the other electrons is what pushes the electron at a velocity quick enough to release it from its attachment to the proton. Alright.
Higher speed.
So again, almost just twice as fast. So just kind of an obvious, this is just about your filter and the fact that the infrared,
and of course white light,
the amount of infrared radiation, it doesn't have as much quanta in it, clearly, and the ultraviolet has twice as much quanta per ray, so you're getting more energy per ray of light. So you're just delivering more energy with the ultraviolet, more quanta of energy, more quanta of momentum. So yeah, let's play the white light just to see how much dramatically faster.
it'll just go to town on.
Right, so the filter is killing a substantial portion of the spectrum of the light, and so each one of the filters is doing a lot of damage to the total quanta that the light is producing. Alright, so then he uses a static ball, which doesn't mean anything. That was just kind of a waste of time, because obviously anything can become charged as, over distance. So that was rather meaningless. And then he's looking at his bookshelf saying how there's no books that have this in it. Well, yeah, there are books, but just because they're not on your shelf doesn't mean nobody's written about it. Lots has been written. Again, Maxwell wrote about this specific subject. There was lots of conversation about the subject. So then he goes to the Wikipedia page. And so,
other than Ken Wheeler's, was they said that it was the heating of the black side different than the heating on the white side. And basically, that's causing more air energy or pressure up against the black side than the white side. So essentially what they're...
So it's obviously, it ends up being a lot more complicated than that simple solution. So, I mean, this is another key subject that comes up is, see, Maxwell has this idea that reflections are twice as much energy, because that's how the formula works out. You know, in a sense, you're taking in energy going this way, and you're giving back something going this way. So that obviously seems like a doubling of the amount of total energy in a system would be a reflection, right? But you have to think about the reflection as an exchange, then you see it differently. And the same thing has to happen on the black surface. So even though it's absorbing the energy, because it's black, and everybody thinks, oh yeah, it's absorbing energy. No, just like everything else, it reaches equilibrium. So unless it's getting hotter and hotter and hotter and hotter, okay, it has a kind of equilibrium it establishes, and once it's at equilibrium, it's going to be radiating as much energy as went in. So it's going to be doing the same thing in the sense that it's going to be giving back the energy. It's just not giving it back in the same form. So you could almost argue the function of this radiometer is, now I'm not saying this is the truth, I'm just saying there's lots of theories you could throw at it. And one of the theories I might throw at it is, is that when the higher frequency light hits the reflective surface, it does reflect off of it, and it stays what it went in. So the silver surface is reflecting the energy. So that is, if blue light hits it, blue light reflects off of it. If red light hits it, red light reflects off of it. And the fact that the blue light is staying blue light, that is the ultraviolet portion or the violet portion of the light, the bluish portion, reflects off the silver side and stays blue. And the blue light transmits very well through the low atmosphere, through the atoms. And the infrared radiation doesn't travel as well. It reflects more. So the blue light reflects less, the red light reflects more. So, I mean, in terms of the molecular thing, the little atoms inside the vacuum. So the idea would be is that the silver surface is reflecting the ultraviolet light back out of the system, back into the glass, where the black surface is taking in ultraviolet light and it's giving back infrared. And the infrared has a harder time getting back to the glass, and even when it gets to the glass, it has a harder time getting through the glass because the glass is a semi-insulator. So the red light doesn't have as easy a time traveling back out of the system. So you end up with more heat on the black side than you do the silver side, because the silver side isn't radiating extra infrared, where the black side is radiating extra infrared because it's converting the ultraviolet portion, the violet portion, the blue portion of the radiation into infrared. So that would be my argument why the black side turns with heat. And that would also explain why when you cool it, it spins the opposite direction. Well, I think it would explain that, but I don't want to add more to this than I need to. But the explanation the official physics people come up with is similar in the sense that thermally the two sides are not equal, and that this is really an edge phenomenon, and it really has to do with the density of the atoms existing. They're supposed to be a centimeter apart or some kind of notion like that, which seems pretty far apart. But anyway, and that's just creating more reflections by the fact that it's thermally a little hotter. And also the idea that if it's any bit hotter, it adds more energy just when you hit it. So if you hit a hot surface, you're automatically going to get a little more energy back because of the heat in the system, and that's going to reflect in your reflection. Your reflection is going to have a little more energy in it because the black surface is hotter. Alright, so we'll play a little bit more of this, but it's just wrong. I mean, Ken Wheeler's an idiot. You shouldn't even bring him up without debunking him rather than almost arguing he's right. And then he argues he's right by pointing out how he was wrong, which is ironic.
They're saying is is that this works very similarly to a Stirling engine.
Well, they really don't do that, so blah, blah, blah. Let's go a little further. I mean, maybe the Wikipedia page says that, but that's not the right answer.
Electric effect. Okay, that's what he's saying, because that's photoelectric effect is the effect where you can knock electrons off of something using light. That's basically what it is, which, you know, putting a little finer point on it than Ken, because for the average person may not know how the photoelectric effect works, that if you could bounce more electrons off of one side than the other, you have a net pressure from electrons exiting, and therefore this would work. But again, getting electrons to leave something works better at higher frequency light than it does for lower frequency light. And so that would add corroboration to Ken Wheeler's understanding of this, that this works by basically the photoelectric effect rather than what they say on Wikipedia, which is the thermal difference in energy, which would be more in the infrared range.
Right, so he thinks because the black surface gets hotter that somehow it should be more sensitive to infrared radiation, which clearly it's not. Black absorbs all of the frequencies. That's the whole idea of the blackness, is all colors are absorbed. So, and the absorption always has to turn into an exchange eventually. Eventually the energy has to be, if it's kept, there has to be the equal and opposite reaction. And so we're just talking about how long that takes, and how long that takes just matters to how fast you reach a thermal equilibrium. So even if the thermal equilibrium is only a half a degree warmer, it's still a half a degree warmer and it's equilibrium. So all of the energy that hits one side is definitely going to have more energy in terms of the fact that it's hitting something hotter, which is automatically has to get hotter in a sense, or it has to give it back. So it's giving it back, and again in a form, I would argue, that is more likely to keep the heat local, which is to keep the pressure near the surface. So that pressure is there's more pressure on one side than there is the other side, therefore it moves. Because the pressure, because now it's infrared, doesn't migrate through the small vacuum as quickly, and therefore it's trapped on the surface of the black side more than it's trapped on the surface of the silver side, and that's why it turns. Okay, so I don't know if there's much else to say about this, but I mean the idea that somehow because black surfaces are radiating more infrared radiation means they're more sensitive, or they're going to be hit, you know, should be in some way affected more, is just nonsense.
In that regard, it's not new. NASA's been experiencing ion propulsion for a while now, but it's not a very efficient propulsion system. But let's just...
If it was ions, the problem would be is they reflect off the glass, they would be doing lots of things, and they'd end up just creating drag because they would pop off of the surface, and then the other arm would smash into them. So you'd end up back at the same problem you have if you take this out of a vacuum. The problem is all the differences are destroyed by the fact that all the atmosphere ends up turning into equilibrium, and you end up with nothing because everything gets hot because there's too many atoms conveying too much information too quickly. So you just end up with drag.
Just go there anyway, just to verify if Ken Wheeler is right or not.
Yeah, he's not right, and you're you're foolish for badly analyzing something he already badly analyzed. So badly analyzing something a second or third time is just a bad idea.
Okay, we just can't sit there and say this is the theory and not doing anything to try to prove it.
So again, he says nobody's done anything to prove it, the blah 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 blah, so, and he wants to, like I said, well, we'll play some more.
Especially since the Stirling engine is compelling, but Ken Wheeler's idea of using different frequencies of light kind of add corroboration that doesn't seem likely because, you know, like I said, if it were thermal, it would be a much lower frequency. This should work with red light better than it works with blue light if it were the Stirling engine effect.
Again, which just doesn't make any sense because you're still hitting both surfaces with the energy. So you'd still have to explain why the black surface somehow does something more with the energy than the silver side does with the energy. And you can't do that with your explanation of the fact that both would be shooting ions the same. I mean, there's no reason to think the black surface would make more ions.
If it works better with blue light than red light, it's more along the lines that it must be something with ionic propulsion. Now, it could also be a combination of the two. Okay, we actually need to go further with this experiment and actually put it in a full vacuum, and then alternatively put it into full air and see how it performs. So,
Already been done.
You know, I'm the kind of guy that will give credit where credit is due.
Right, that's just plain stupid because Ken Wheeler's wrong, his whole theory is wrong, his whole understanding of what a photon is wrong. Alright, well somewhere in here he says this whole thing about, you know, buy me, you know, buy me the equipment so I can do the experiment that's already been done and done very professionally and well. So let's play that video. So this is Applied Science, a channel I am subscribed to. He makes very straightforward videos. I can't say there might not be something he says I don't like, but most of it's pretty straightforward.
If you've been to the gift shop at a science museum, you've probably seen one of these. This is a Crookes radiometer, and it works like this. If we shine light on it, the radiometer starts to spin, and the brighter the light, the quicker it spins. But what actually makes it spin? You might be tempted to think that it has something to do with the photons themselves. So the photons that are emitted by the light bulb hit the radiometer, and it's actually the momentum of the photons that cause it.
Okay, so this
refrigerant. And what I'm going to do is tip it upside down and spray some of the refrigerant on the glass envelope of the radiometer. And as you can see, it's actually spinning backwards relative to the way that it was spinning when we shined the light bulb on it.
So the sensible perception would be now he's absorbing the heat from the environment in the sense that the cold surface is now not at thermal equilibrium, so it's going to absorb heat, and that affects the silver side more than the black side in terms of well, yeah, it depends on how you look at it, I suppose. I mean, it just changes the temperature differential in the sense that you're just almost creating the opposite effect, because now it's not what the surfaces are radiating, it's what they're losing. So it's not what they're gaining, it's both those surfaces are now losing their thermal equilibrium. So they are both losing energy, and the one side, I guess it would have to be the black side again, this time, just as it absorbed energy more readily, it's losing energy more readily. So that's why it's spinning in the opposite direction, is because now the black side is losing energy faster than the silver side.
So clearly there is something else going on here. If it were just a photon effect, making the glass envelope cold would not cause it to spin backwards, because we aren't pulling photons out.
Well, you sort of are pulling photons out, so that's really, you know, it all depends on what you think a photon is. And so much of the energy, in terms of the heat, is in the form of infrared photons. So it's in the form of electromagnetic radiation. I mean, all the radiation essentially is. That's the only way it can travel through vacuums and all this other stuff is it has to sort of be in the form of a photon. So the only way the surface of the glass can communicate with the surfaces of the radiometer is it has to communicate with photons. There's no other way for the temperature differences to be transmitted to each other than through a force capable of migrating through vacuum, which are photons. There's nothing else that can do that.
Out that way. As you might have guessed, the effect is thermal, and it does require that there be some gas in the radiometer envelope.
So again, thermal is still photons. So again, it's still about light. It's just light we can't see. So you're just really talking about the fact that one side converts ultraviolet radiation or blue light into red light, and one side doesn't. Into infrared, and that the infrared photons are the ones that are really affecting the device, and not in the way, not in some special way, just in a way that there's actually more of them are staying near the surface. They don't get away. They don't allow the thermal difference to be transmitted at the same rate. The heat can't escape the black side as fast as the heat escapes the silver side, technically. And by heat, I mean the energy, whether in the form of ultraviolet light or in the form of infrared.
If there were no gas at all inside here, then the only thing that could touch the rotor and make it spin would be the photons shining on it. And we've determined that can't be right because the photons would be making it spin the other way. We also know that it doesn't work if we're just at ambient pressure. So if we just broke this glass envelope and shined light on this, it wouldn't spin. The gift stores would be unhappy because they wouldn't be able to sell you this neat little glass envelope. So that means that there must be some ideal pressure at which the thing works really well. It can't be zero, and it can't be ambient pressure. So I've set up my vacuum chamber here with a vacuum gauge, and the radiometer. I actually broke one of these.
Probably he's talking way too much than is necessary here. So the point is he breaks it, puts it inside a better vacuum chamber, goes to a very low vacuum, and it doesn't spin.
This thermal effect, and there's nothing to make the rotor spin. Now I'm going to raise the chamber pressure slowly by opening an electronic valve.
And it starts to spin.
As you can see, it's now...
So now he's let in a few atoms, to increase the number of atoms inside the chamber. And by increasing the number of atoms, now there can be surface interactions. Now you can have the effect of the surface area, the atmosphere around the black can now be different than the atmosphere around the silver.
Now spinning, I can measure the exact rotational speed with the optical tachometer that's inside the vacuum chamber and get the readout from the oscilloscope here.
Yeah, this is sort of not very intuitively, it doesn't say much. 2.6 volts doesn't really tell you much about, here's his chart. So this is complete vacuum, this is no vacuum. So you have some effect at a complete vacuum, I guess. This is 20, it's zero's way down here, so I don't know exactly what that means, but clearly it doesn't move. So whatever this 20 means, it doesn't mean much. And so I guess this is the amount of vacuum there is. No. This is the amount of movement versus air pressure this way. This is air pressure. Well, anyway, so you get the most speed at just a little bit shy of a good vacuum, and then it slows down the more air you let in from that peak. It just declines and declines until it goes back to zero, or some imperceptible, it's not moving number. Not a great chart, actually, but anyway, it's okay. It's probably easier to see with his raw numbers, but anyway, the fact that he did it, very good. So what else do I say? Yeah, so I think that's about all that's interesting here. I could play a little of this, but I don't think it'll say much.
We now have our data, and just as we suspected, the radiometer doesn't spin at very low pressures, and it doesn't spin at very high pressures, but there's this perfect balance point, which in this case corresponds to about...
So I suppose he pumped it up above. Yeah, this is 1.2 atmospheres. Okay, so here's 1 atmosphere. So it doesn't spin at regular air pressure.
About 7 millitorr. And that means that a gas molecule travels about 1 centimeter before hitting another gas molecule, just to give you an idea of how dense the environment is inside the chamber. For comparison, at ambient pressures, I think the distance is about 100 nanometers, so quite a bit less dense than ambient pressure.
But just dense enough to allow the infrared radiation, I would argue, to stay local on the black surface. And that's all you need to create the differential between the two surfaces, front and back, not side to side. And so like the lift on a wing, you have enough of a pressure differential on the two sides that one side will be pushed by its local atmosphere. And so it's almost a buoyancy argument again, in a sense. So anyway, so it's already been done. You don't need to redo it. He did it very well. It's a very nice little experiment he did. Nice equipment, very fancy, very sophisticated, quite adequate to the cause. So yes, we don't need to redo this one. Maybe you could fill it with some other kind of gas, you know, helium or something, see if that makes a difference. Might be interesting, I don't know. But anyway, so that's probably enough. So just 2 crappy videos, you know, just making more noise, you know, not making the physics more clear and more precise, not building the foundations out of cement, you know, keeping everything mushy and wobbly, and you know, not doing a proper investigation. You know, again, this is about detective work. That's what physics is. It's detective work. And you got to analyze your samples and make sure your fingerprints aren't smudged, or that somebody couldn't have put a little bit of fake latex on their finger and made a fake fingerprint. You got to do lots of tests to see if you're getting fooled. You see a little bar pattern, you don't jump to conclusions and start going, oh, it's an interference pattern, this is on and off. The simplest pattern in the universe. Yeah, you don't get fooled by that kind of crap. You know, if you're an experienced detective, you know, you've seen that crap before. You've seen those false dodges. You don't fall for that crap. So anyway, I think that I've said what I need to say. Yeah, so there are a couple of complex subjects. The one is the idea of what a reflection is, and the fact that everything, in a sense, every action has a reaction eventually, and that's sort of the trick of what I was talking. I'm always talking about trapping stuff. The idea is if you trap it, then you've changed your thermal equation, in a sense. You've changed, you're not at equilibrium, you're gaining something, you're gaining velocity, you're gaining something. And and so it's never really about the fact that there will be the equal but opposite reaction. The question is can it be delayed? And I guess that's sort of the argument, is you can change the form of the reaction, and that can matter. So I mean, you always have to obey the conservation laws, but the truth is absorption is always going to be the same as a reflection, in a sense, realistically. Is it sort of the way electrons work? Electrons can't move without giving back what they take. They always absorb and reflect. They always reflect, so to speak, the electromagnetic spectrum. But the question is when they do that inside of something, the reflection can get trapped for quite a while before the reflection actually gets out of the atom, that kind of thing. The atoms themselves can hold the reflection and store it, and then release it all at once. That kind of thing. Okay, so I think, you know, so that's one complex subject. The second complex subject is the nature of the ultraviolet photoelectric effect, and why, what exactly is happening. And again, so this is where physics has an obvious continuity problem. They draw photons as a few waves with nodes, and then they talk about an ultraviolet photon. Well, what is that? How many nodes is a photon? And then you wouldn't call that a quanta, because the nodes are the quanta. And so clearly when ultraviolet light's knocking an electron out, it probably can't be, okay, just 2 nodes of ultraviolet. It probably has to be a certain amount of ultraviolet. The rays have to have a certain integrity. Just like our eyes need a certain amount of photon ray to hit them for it to register it as a photon, you're not going to get the photoelectric effect if your ray isn't substantial enough. Alright, that's probably enough of that. But, you know, they're too kind of complex. I mean, the subjects get complicated in the sense that you have to understand them based on what the nuclear bits are doing, based on what some elemental thing is doing with the energy, and that the energy is always in a form of indestructible momentum, so that it's always in some traceable bit, that you have to just account for the traceable bits that are the event. And how else to say that? And in the universe, there's a for every bit going this way, there's a bit going this way. And in a sense, you can't, the absorption is dependent on that interaction with the 2 bits. How to say that? You can't keep this without giving that. But anyway, till the next video and such. Till the next, whoever will be the next victim of my critique. I'm just saying, it's just, you know, I don't have anything against the Cine guy, except, well, the fact that he's wrong, and, you know, I'd probably hate his whole ethereal mechanics. Just sounds, you know, way too unicorn bullshit. You know, the whole ether thing is such a dead subject. I wonder what these spark plugs are for. Interesting. I mean, there's a whole bunch of spark plugs in here. There are spark plugs. I can see the bottom of them has the typical spark plug kind of thing. One assumes they're for vacuum hoses or something, but it is weird. They do look like spark plugs. Well, anyway, just saying, that's what they look like. I mean, this is a weird chamber here. It has 2 kinds of vacuum. I mean, here's a fan that pumps stuff out, and I guess this is the other kind of vacuum. It does some other kind of weird thing to pull the little ions out. But even that's a whole another kind of theoretical subject where you get into the complexity of how you actually create a very good vacuum, in the sense that how do you vacuum things? I mean, once you've got so few, how do you put a magnet in to pull anything out? You know, how do you even tie strings to your magnet? In a sense, that's what you're trying to do, right? You're trying to take out bits that you'll attach to something by charge. And it's only through charge you can pull things out. That's the only mechanism there is charge. And technically, you know, you pull on an atom and it's attached to another atom because of charge. So, you know, you're always relying on the proton and electron relationship. I mean, that's another subject I go into, because that's another one people just don't get. You know, but when I talk about surfaces, you know, and the fact that electrons, you know, they say the word free electron, like, okay, so they have some idea that there are these electrons that are free, but there really aren't free electrons like they're flying through the atmosphere right now. Those aren't free ones. Those are ones that have been ejected at some velocity, if there are any loose ones. But electrons look for a proton really quickly. I mean, they're really affected by the charge, and any difference in the charge, they'll bend their path to fall into the proton. I mean, they love protons and they hate electrons. And so atoms aren't doing something special where the electrons are absorbing all of the proton's energy and no other energy gets out. So it's, like I said, it's like our solar system. There's a bunch of comets, you know, like Pluto type, far away, loosely attached things. And there's a bunch of them that can be around, you know, lingering out there. You know, where we can only see some tiny portion that, you know, ellipse close enough for us to see them, and they do it within the last 1,000 years when we had some hope of seeing them. You know, probably the last 200 would be more important, or 100 for some of them. You couldn't even see them 1,000 years ago because it's too small. But there's a ton of those. And the same thing's going to happen on the surface of a material. So there's going to be a bunch of electrons that aren't part of the atoms, but they're still attached to the proton. They still sense the proton's there. And they hate the electrons that are part of the surface of the atom, but they're still attached to the proton. So they're still going to hang around. They're just not hanging around very strongly. I think that's a huge part of this whole photon physics and understanding the two-slit experiment and all this stuff, is the fact that, yeah, that's what electrons are going to do. And electrons aren't going to do, they're not doing orbiting crap. They're just going to hang around where they feel the proton. They're just going to sit in that position. And then they don't like each other, so the next electron is going to be a certain distance away, and the next electron will be a certain distance away, and they'll just fill up a whole grid. On the surface of all things, there's going to be a little grid of electrons that are automatically just going to start filling the empty chairs that are there. There's a little bit of proton energy to take advantage of, and they're going to take advantage of it. You know, proton low pressure, if you want to call it that. So anyway, I think I did my job here. So again, I don't have anything personal against this guy. It's just bad physics is bad physics, and I think it should be pointed out on the professionals are making a mess of it, and the amateurs show up and they don't save the day. Because they end up doing the same crap where they start saying things that are just not true. And that doesn't help. So anyway, yeah. Till next time and such, so forth and whatnot. So enjoy the weekly award you won and such. So yeah, I mean, there's a lot of things for me not to like, though. It's not like I don't have anything personal against this guy, but I really hate these Patreon shit, this whole, you know, again, this just extorting and bribing people to play along. I mean, can't we do better than that? I mean, I know I have a contest, you know, bribing people. But clearly they get rewarded with something that's real. Okay, not like, here's a gift, you know, my fingerprint. I'll do my fingerprint on a piece of paper, send it to you. It'll be really cool. You can look at it under a magnifying glass. It'll be really interesting. I mean, you know, it's not exactly a real reward. Oh, he's going to give me the source code. Ooh, to a program that doesn't work. Great. Anyway, so I think I did my job. Didn't I? Yeah, I think I have completed the task here. So, yeah, clearly my contest doesn't require people to pay. So, you know, clearly I'm the one paying, not them. You know, so, big difference. No ads. You know, that kind of thing. Big difference. Anyway, okay, so that's enough. So till the next time. I mean, not that I wouldn't mind soliciting money. You know, I mean, if somebody sends me money so I can buy stuff to do physics experiments, cool. Appreciate it. But, you know, unless I'm going to do something, again, see, this is just why do something that's already been done, right? Until I have an experiment, I just know I can do it, and I can do it cheap enough to make it worthwhile for me to do it, then yeah, I'm not going to ask for anything. So if I can think of an experiment that'll actually prove something that's just, you know, that's moderately not too expensive and that has something to do with my expertise, like I said, I mean, I could do I could do the radar double slit experiment, the microwave one, but I'm just not technically good enough, you know, to be able to do all this high frequency detection stuff. It's a little bit too sensitive a thing. It's just, yeah, it's not my expertise. So it's better if somebody who knows what the fuck they're doing does it. So anyway, till the next time, such.